All right, we are in kinetics. This is now the second video of chapter 13. We are going to be looking now at the energies involved as a reaction takes place. And we're going to hit some key terms that we have talked about previously, but we're going to bring them up again and look at energy profiles with those. So getting started. All right, we need to talk about chemical energies. We'll usually have a net change in energy. Either energy can be released or absorbed. Example here is nitroglycerin. This is dynamite. Okay. Alfred Nobel is a person who has worked with nitroglycerin to get it into a form of dynamite that then can be used to blast rocks and mines. A very important thing there. Nitroglycerin itself, very unstable. Okay, so just a little bit of movement can shake this off, get this started, and this is a very explosive reaction producing a lot of heat and energy. All right, you can see 5,720 kilojoules per mole there. 4 molecules of the nitroglycerin, and if you count up the total number of molecules it produces of the gas, this is very explosive. All right, so this would be an example of a exothermic reaction. You can see that the energy is listed on the right-hand side. It is a product. So if you have a reaction that releases energy, your energy is a product, exothermic. Endothermic then needs to absorb energy from the surroundings, so the energy is listed on the reactant side. And then you have some reactions that are energy neutral. Overall, there's no net change in energy loss or gain. All right, so if they are releasing energy, okay, what is going on here? So where is this energy stored? Put that down. Energy is stored in the bonds, okay, of the reactants and the products. We have talked about this before, but any time that you have to break apart a bond, okay, you're breaking apart a covalent bond, ionic bond, whatever, anytime you're breaking it apart, that requires energy. All right, so if you look at this first picture up here, if you break it apart, you see those little energy things coming in. You're just taking energy to break them apart. Now we have the individual atoms. The individual atoms now come together, form new compounds. So here's now forming product. Anytime you form a bond, you're releasing energy. All right, so it's a play on that. How much energy does it take to break the bonds versus how much energy is released when forming, and that will determine if you have an overall exothermic or endothermic reaction. All right, the bottom picture, you can see the molecule AA, and you have B2 there as well. The first example, it takes a lot of energy to break apart the reactants. And then when you form the products, it just releases a little bit. The energy you had to put in to initially break is greater, so this would be an endothermic. The bottom picture, it takes a little bit of energy. It still takes energy to break apart the reactants, but when the new products form, it releases a lot of energy, so this would be an exothermic reaction. All right, moving the slide over. Let's look at these energy profiles and how this looks. All right, so the energy profile, there is a reaction coordinate on the X. So this is basically saying you start here and you finish here. And if we start at the reactants, we finish at the products. And then over here we have energy, high in energy up top, lower on energy in the bottom. All right, so when you have a exothermic reaction, the energy of the products is lower than the energy of the reactions. So that we say this will go downhill. So from reactants to products, we lower in energy. When you calculate this, the change in energy, that triangle there, change in energy for the reaction is negative. You take products minus reactants, you will get a negative value there for exothermic. All right, looking at the example then for a endothermic, okay, the reactants are lower in energy and the products are higher in energy, okay? This means then it's going to require more energy to break apart the reactants than you release when you form the products. So this now, if you take products minus reactants, you are going to have a change in reaction that is positive for a endothermic reaction. All right, let's go and look at this thing right here. I want you to try to answer these questions based on what we just talked about and see if you can get these 6 things answered, and then we'll come back and we'll compare our answers. All right, you should have gotten this filled out as well, and you can see from looking where the reactants start and where the products are that this has gone downhill, so it's an exothermic reaction. Since an exothermic reaction gives off heat, it will feel hot to the touch, okay? So opposite to that, endothermic absorbs heat, okay? Heat has to be put in, so it will actually feel cool to the touch. You can calculate the change in energy for the reactants. You take the energy of the products minus the reactants. And this is a case where the sign is important. You need to have a positive or a negative sign regardless of what the number is. Always make sure you have that sign as well. So this would be a negative 40 kilojoules per mole, which is what we expect, okay, it to be negative for an exothermic reaction. And just looking at the energy of reactants up high at A to the products down here at B, you can see that the reactants are higher in energy. Reaction again goes downhill as it goes from reactants to products. And then here's an important thing. If you were going to take the opposite reaction, so the reverse, this is going from A to B, but let's say we wanted to go from B to A, what would the change of the energy be for that reaction? All right, and so the energy change for reverse would just be the negative of the change in energy for the forward. Since our forward was minus 40, the negative 40 would be a positive 40 kilojoules. So it's just opposite in sign to get the change in energy for the reverse. All right, that's it for this lecture. We're going to be looking at a couple more things adding to this to continue on in our chapter about kinetics next.